I'd like to welcome everybody to this thesis presentation. The title is Agile Manufacturing System Scheduling Using Genetic Algorithms and Simulated Annealing. My name is Sherif Masoud, the supervisor is Dr. Lutfi Gam. These are the contents of the presentation. It consists of introduction, background, problem description, objectives, literature review, Agile Manufacturing Systems, and AMS scheduling methodology. I'm going to describe the 4 developed heuristics in this research, which are GAs and SA based, and I'm also going to describe the computational experiment, and then the resultant discussion includes verification, numerical results, DLB or the percentage deviation from the lower bound, and the frequency of resulting in the best solution, and then I'm going to point out the significant factors and interactions, and I'm going to talk about FGGA results or the GGA results, frequency of resulting in the best solution. And then finally I'll end with the conclusion, including the summary conclusion, validation, and 2 points for future research. First, the background. Agile manufacturing is considered as the latest manufacturing paradigm. That term was coined in the year 1991. If we look at manufacturing from the beginning of history, it first had the form of craft production, which is about highly skilled workers using simple tools to produce customized products, and then mass production after the introduction of interchangeable parts and division of labor and other significant contributions. Mass production was introduced towards the beginning of the 20th century, and then lean production was introduced to deal with the waste of mass production. And finally, agile manufacturing, which is about, if we summarize it in 2 words, it's about product variety and quick delivery of products to markets. This thesis is about the scheduling of a certain problem. The problem is about this manufacturing system consisting of machining stage and an assembly stage. The raw material enters the first stage consisting of a single machine, resulting in parts, different parts, that are assembled in various ways by several parallel identical assembly stations to, at the end, get finished products. The objective of this scheduling problem is to minimize the mix spend, which is important in the context of agile manufacturing. So this system satisfies the variety, it produces a variety of products, and it also, the mix spend is minimized, so this is done quickly. In the manufacturing system described, there are 2 types of products that can be manufactured. These are simple products and complex products. Simple products are described by simple diagrams, such as part A of this figure, and then complex products are described by complex diagrams, such as part B in this figure. The simple diagram is a diagram in which at any assembly level there is no more than 1 assembly node, such as this one. And then the complex diagram, at least it's the opposite. So at least in 1 assembly level there is more than 1 assembly node. The first scheduling problem to schedule this the manufacturing of this type of product can be solved optimally by heuristics in literature. However, the second one, the complex product scheduling problem, for it, the ultimate solutions cannot be guaranteed by any method in literature. Therefore, this thesis focuses on the complex product scheduling problem and simulated annealing algorithms to solve this problem. And then to plan, design, and implement a two-to-third factorial experiment replicated twice to compare between the available heuristics, the existing heuristics, and the proposed ones, and also to identify the significant factors and interactions. A very good paper that reviewed research on agile manufacturing systems is the one by Sanchez and Nagy, which was published in 2001. They provided a classification scheme for research on agile manufacturing. So agile manufacturing, as can be seen here, has various research areas. These are 9 areas, including product and manufacturing system design, process planning, production planning, scheduling and control, process design, and so on. So they cover the whole aspects of a modern enterprise, including industrial applications, engineering and business applications, information systems, and so on. So this thesis belongs to the area of production planning, scheduling and control, in which only 4 papers were published dealing with the scheduling of agile manufacturing systems, or in this area in general. Again, the paper, the problem described in this thesis was solved in literature before in the paper by he and Baden, published in 2002. We provided 3 heuristic algorithms in which this is scheduled for HA1, heuristic algorithm 1, which was described in that paper. The system consists of single machine and then 2 identical assembly stations. This schedule has a makespan of 38 because the time of completing the last assembly operation is 38. They also introduced a lower bound. The lower bound is equal to 37 for that particular instance. Of course, this instance has a diagram associated with it describing the product being manufactured. It consists of 4 parts and 7 assembly stations, but the diagram is not shown here. So in this research, 4 algorithms are proposed. The first one is general genetic algorithm, or GGA, in which the representation of the problem is a fragmentation of unrepeated numbers with the size n from 1 to n, where n is equal to the number of part nodes on the diagram. The evaluation function is the mixed span. The initial population is evaluated randomly. The method of selection used is well-trained and list selection. There are focus over 3 mutations. The population size was specified to be 56, and the maximum number of generations is equal to 54, resulting in 3024 objective function evaluations maximum, which is equal to 56 times 54. It's said maximum because the lower bound is computed whenever the lower bound is reached. The algorithm is stopped because this means that the optimum is reached. Again, so this is the representation. This is an instance having 5 parts. This is sample chromosome in GGA. This chromosome can be decoded or translated to this schedule. The system again consists of a single machine, 2 assembly stations, 5 parts, and 15 assembly operations. It has an exponent of 46. The chromosome dictates the schedule of the single machine. So we have 6, 1, 4, and then here T6, T1, and then T4 back-to-back single machine scheduling. And then the assembly operations are scheduled on AS1, AS2, first come, first serve. Whenever there's an assembly station available, we scan the assembly operations and define the ones with the specified preceding parts or assemblies, specified constraints, and then we schedule it, because this means that this assembly operation is ready to schedule, rather than schedule. As I said, GGA has 4 crossovers and 3 mutations. This is an example of LOX, linear order crossovers. It's one of them. In any crossover in GAs, in general, we have 2 parents, which result in 2 children. In this case, these are P1 and P2, and these are the intermediate steps. These are P1 and P2, the 2 children. So here, two points are chosen randomly, and between them, we highlight the section between them, and then in one parent, we replace the entries which are equal to the cut section. I call the middle section cut section. So in one parent, the entries that are equal to the ones in the cut section in the other parent are replaced with B's, meaning centrally vacant positions, and then those B's are split towards the center one by one. And then finally, the final step is to replace the B's in the middle section by the other entries in the other parent in the cut section in the other parent. So this is one of them. There are in general a total of 4 crossovers and 3 mutations. This is one example of a crossover. GSA is general simulated annealing, the second algorithm described here. It uses the same representation, the permutation of unrepeated numbers equal to size n. The initial solution is done randomly. The evaluation function is the mixed span, and the maximum number of project function evaluation is equal to 324. The same figure used for GGA for pair comparison. This is a maximum of 504 iterations, because at every iteration the objective function is evaluated 6 times. So 6 times 504 is equal to 3024. In GSA, the best move strategy is implemented, meaning that at every iteration we have a solution, we call the current solution. We use 6 different perturbation schemes to obtain 6 different solutions from the current solution, and then we evaluate those 6 solutions. We determine the best one, the one with the least mixed span. We call it the proposed solution, and that if that proposed solution is better than the current solution, we go ahead and replace it. If it is not, we compute the progress accepting it. So it goes by this sequence. First, we compute T sub k, which is called the cooling schedule, equal to gamma constant. to the power of iterations, the current number of iterations times T1, another constant. Gamma in this research is equal to 0.9 and T1 is equal to 150. And then we run the compute delta F, which is equal to the F1 and F0, which is F proposed minus F current. And if delta F less than or equal to 0, meaning that the proposed solution is better, we PR the probability equal to 1. We accept it. We accept that move. If it is not, we compute this probability function, e to the power exponent minus delta F over T sub k, and we generate a random number between 0 and 1. If that number is below that function, we will have to accept it. Now the probability of accepting the worst solution decreases over the number of iterations because we do not want to lose the information gained in research, in our search towards the optimum after a large number of iterations. Now, as a type, there are 6 perturbation schemes. This is an example of PS6, in which the subsequence is moved and or reversed. In this case, it is both moved and reversed. We can see that the 245 is first moved by 2, shifted by 2 entries to the right, and then it's reversed 542 into 245. So this is a solution obtained from that one by PS6. The third and fourth heuristics proposed in this research are heuristic assisted genetic algorithm and heuristic assisted simulated annealing. In HAGA, everything is the same as in GGA. However, one chromosome in the initial population is obtained from HA. HA represents the old heuristic, the existing heuristic that existed in literature before this research. In HASA, heuristic assisted simulated annealing, everything is the same as in GSA, except that the initial solution is obtained from HA. Now I'd like to talk about the computational experiment. It's a 2 to the third factorial experiment replicated twice. The responses are the percentage deviation from the lower bound and the frequency of resulting in the best solution. The fixed effects model was used. The factors are number of part nodes in the graph, complexity of graph, and the ratio of average machining time per part to average sub-assembly time per sub-assembly operation. This shows us the different combinations in the computational experiment. As you can see, factor A varies between 16 part nodes and 32 part nodes. Factor B varies between low complexity and high complexity, and factor C is either half or 2. This is the ratio factor. There are 8 combinations run, and then the codes were developed to implement those heuristics and the old one as well, and the lower bound. It was the objective function in research, which is the function given a permutation. A permutation is entered to the objective function, and it gives us a schedule with no make sense. So the objective function was verified. It was used in all heuristics as well as the old one. It was verified to be correct by comparing it to problems with no solutions as well as hand calculations. In addition, this figure is just a sample for a problem. It shows us the HA solution supported the constant, 160 in this case, and the lower bound 151. And this in the one in gray is HAGA, heuristic assisted genetic algorithm, and GGA is in blue. It shows us over the number of generations the best objective function value for every generation. So the result, of course, that it's never happened that any mixed span is below the lower bound, because this is not possible. It's not acceptable. It's not possible. This is the same figure for the simulated annealing-based heuristics. Again, we have the lower bound in red and the HA solution in green, and the performance of HASA and GSA in gray and blue. We can see, of course, that unlike GGA and HAGA, the objective function value is allowed to increase in simulated annealing-based algorithm. This is a characteristic of SA, simulated annealing, because it's one of the advantages of simulated annealing because it allows to escape from local optima. The numerical results, these are the 8 runs in the experiment with the 8 combinations. There are 10 responses. The 10 responses belong to one of 2 types. The first type is the percentage deviation from the lower bound, and the other one is the frequency of resulting in the best solution. It can be shown here that in run 1, what is the best heuristic is GSA, because GGSA is lowest, because the D type of response is lower the better, so GGSA is the best one. And also FGSA is the best one, because the F type response is perhaps the better, so GSA in general is the best one for run 1. In run 2 and run 3, HASA is the best, and then run 4, GSA again is the best, and then run 5, the problem becomes easy and all 5 heuristics can result in optimal solutions. We know that because the deviation from the lower bound is equal to 0. So there is no possibility that any better solutions are found. So we know these are the optimum. Of course, in this figure also shown is the power of factor C. When C changes from half to 2, problem becomes easy and all 5 heuristics can solve it optimally. These are common statistics for the percentage deviation from the lower bound for the 5 heuristics. The minimum for all of them is 0. The maximum for HA is above 20%. However, for the other proposed 4 heuristics, it's below 10%. The mean also is shown and the standard deviation as well. The best heuristic is GSA because it has the minimum values for all 4 statistics, followed by HASA. This figure shows us the number of instances of the percentage deviation from the lower bound falling in one of 4 ranges. As shown in that table, R1 is when DLB, percentage deviation from the lower bound, is between 0 and 1, R2 when DLB is between 1 and 3, R3 is when DLB is between 3 and 10, and R4 is when DLB is above 10. We can show that it is shown that the 4 proposed heuristics outperform HA when the range is below 1%. And then for the 4 proposed heuristics, the non-gray ones or the colored ones, the trend is decreasing number of instances as the range shifts away from the lower bound. However, that's not true for HA. For example, it increases from R2 to R3, and at R4 when there is no one instance of the 4 proposed heuristics falls in R4, HA has some instances falling in that range, which is very hard for us. Frequency of adopting the best solution. Now this graph shows us the frequency of adopting the best solution in terms of number of instances for the 5 proposed heuristics. It's shown that the 4 proposed heuristics beat the old heuristic. This table shows the significant factors and interactions for the 10 responses. I'd like to point out that FGSA and FHASA are most robust because they are only affected by factor C. They aren't affected by any other factors or interactions. So they are most robust. In addition to that, numerically they resulted in the best results. So they are expected to perform best in the most difficult instances of that problem. And of course, other significant factors and interactions are given for the rest of responses. As an example, this is the GGA frequency of resulting in the best solution. And that's the variance for it. Just to illustrate, it's of course it's shown here that factors AC and interaction AC are significant because the probability greater than F is below 0.0001, which is below 1%. So they are significant at even a much higher level than 5%. And then this is the AC interaction graph for FGGA, GGA frequency of adopting the best solution. Interaction graph at B is equal to low, and the one that is for 32-part node, in black for 16-part node. So you can see that when T changes from 0.5 to 2, no matter what any factor is at what level, the response increases. Alright, so the power factor C is very shown here, it's very clear. And just one point, that factor B, for FGGA it was shown in the previous slide that the only significant terms are A, C, and AC. So factor B is not significant. So this is at B is equal to low. we can see the same graph as well, very similar at b is equal to high. So nothing changed because b has no effect. And also one more point. This performance type is the higher the better. So for the black line is above the red line. So this means that when a is equal to 16 part nodes, the response is better. Meaning that this is expected because as the number of part nodes decreases, search space decreases, which is equal to n factorial, and algorithms like genetic algorithms are expected to perform better. These are the summary and conclusions for the presentation. It's about scheduling an agile manufacturing system with machining and assembly operations. To solve that problem, 4 GAs and SA-based heuristics were proposed. A computational experiment was also implemented to compare between all available heuristics. The two responses are the percentage deviation from low down and frequency of resulting in the best solution. It was shown that the proposed heuristics perform better than existing ones. Average machine time to part to average assembly time to assembly operation was shown to be most significant factor, and the higher better of it. The SA-based heuristics were shown to be most robust with best performance. Finally, the validation here is the results of this research were validated by statistical means such as abnormal probability plots and outlier t-plots, because this was used to validate the results of the computational experiment. And I'd like to say that all results are perceived to be valid only for DNS structure described, and with that problem description and a function. And as the scheduling problem parameters change, it's not expected that the results will be valid by high confidence. 2 points for future research. This research can be extended to schedule an AMS with a single machine in stage 1 and multiple assembly stations in stage 2. The same structure is here, but with adding the assumption of sequence-dependent center time. Another point is to schedule an AMS with different structure, consisting of flow shots in the first stage and multiple assembly stations in the second stage. Thank you.
Thank you.